small signal equivalent with current source based load. Load current. So let us see how the small signal equivalent will change with respect to that. So when we say RD is current source will go away because it is infinite resistance. Now because that goes away, the impact of R0 is also reduced. In this case here, KVL is not needed. This KVL will exist as it is. What does this become now? In this case, you will apply only KCL here. If you apply KCL at this node, KCL at output node, and KVL will come here. So with KVL, what are the learnings you have? V1 plus Vin equal to 0. And in this case, you will get okay. One other factor which I wanted to tell you was the absence of channel length modulation. No CLM. No channel length modulation. This implies lambda is 0. This implies R0 is infinity, right? No channel length modulation. Another factor is constant current source. Constant current source at the top node. So what do you get here? Vin, let's come back again. KVL will be V1 plus Vin equal to 0. What else? KCL when you apply, at KCL I will get GM plus GMB times V1 is equal to minus V out by RD. Or can just keep it here and say V out by RD equal to 0. So if you take these two conditions, you get your AV is V out by V in times GM plus GMB times RD. Or that is equal to 1 plus eta times GMRD. So this again shows that the non-inverting characteristic is present and also the output there. Now there are, as we find out, next we will have to find out what is the input impedance. What is input impedance here? Input impedance, where do you see? Input impedance is seen over here. So what is the input impedance seen at this particular stage? What is the circuit that determines input impedance? We will draw it here quickly. RD. VB, this is M1. There is a channel length modulation is present. So there is an output impedance R0. And this is the input impedance Rin that you see. So what will be the R in that? To measure R in, you can apply a test voltage and a test source. Vx directly apply at this point. This will be Ix. So we will find out Rn as Vx minus Is. So apply again same thing, and if you apply KVL, yes, we have the output impedance here R0. So if you apply KVL in the first loop, you get V1 is equal to minus Vx. Remember, we will have to remove this resistor here because we are biasing using a constant current source. So there is no resistor into the picture. Then what is the other Vx test that we get? Apply KVL in this loop. Right? When you are applying KVL, KVL inside loop, KVL at the outside loop, that you get RD times Ix, total current, right, plus R0 times Ix minus Gm plus Gmb times Vx is equal to final value Vx. Now if you simplify both these and get V in as Vx over Ix, and that is given as Rd plus R0 over 1 plus Gm plus Gmb R0. Now this, if you can simplify just to get understanding, you can equivalently write it as Rd divided by 1 plus Gm plus Gmb R0. You can remove this one. So it will be Rd by Gm plus Gmb R0 plus, now when you have R0 by Gm plus Gmb plus R0, you will have R0 will cancel with each other. So you'll have this term 1 plus Gm plus Gmb. So few conditions that you can quickly absorb and understand. First thing is, let us understand what are the special conditions that we will see. One of the conditions is if Rd is short circuited, what happens is Rd is 0. The moment Rd is 0, what is left over with this? Take this effective. You have Rn is R0 over 1 plus Gm plus Gmb plus R0. Sorry, times R0. And what happens if your Rd is a ideal current source? If your ideal current source, Rd is infinite. So your Rn will be infinite. So what happens is, if your input impedance is an realistic value, then only you have ideal current source or common gate stage is low impedance. Otherwise, the common gate impedance will always be high itself. So the Rin of Cg is low only if the load impedance is low, which is at the drain. If you do any other ideal amplification, you will get Rn is infinity. So you need to carefully understand. So this is the common thing with this. Common stage, right? Sorry, common source amplifier, Rn is always infinity because this input is applied to the gate. In this case, if your load is low, then your Rn also is low. So that is one understanding that you have to do. Now, what is the output impedance? Output impedance you will get from the gain circuit. It is brought here. Output impedance will be 1 plus GMB plus GMB, that is this R0 plus GMB times R naught, this value multiplied by the RS. Now that will be in parallel with RD. So this will be your output impedance. Understood? Now let us do a quick example to understand what we have read till now. Because learning by example is my favorite way of learning. So what is the example we can do? We will say for a typical exam question, if you say find out what is the small signal amplifier for this kind of a circuit. It's the first time you're seeing cascaded devices, but this cascade device is familiar to you. What is that cascade device? We have device M2, device M1. At the gate of M1, we will apply the input and RD. If you note, one is an NMOS device, M2 is a PMOS device. Now what is M2 connected as? M2 is connected as diode connected, right? Diode connected means its effective impedance looking into the rays is 1 over GM. It is in the edge of saturation, so you can use the saturation drain current equation as a load. Okay, and you will also have channel length modulation will also be there. So you'll also have R naught. So this R naught is going to be 1 over GM value. So we have to do two considerations. We can do is one in the presence of channel length modulation, another in the absence of channel length modulation. So let us start when channel length modulation is 0. Okay, the question is find the gain, open loop gain in the circuit. Find the small signal voltage gain. Find the small signal voltage gain when channel length modulation is absent and present. So AV when CLM is 0 and AV when CLM is non-zero, that is, it is present. Let us begin. How do we start off with this? First, we need to draw a small signal equivalent. How do you begin with that? When lambda is equal to 0, that's our case 1. Channel length modulation is 0, so lambda is equal to 0, and this is for both M1 and M2. So in that case, what do we infer? M2 will become 1 over GM2 load, right? Small signal load due to the single stage amplifier and is a diode connected load. Now let us quickly draw the small signal equivalent. How does that look? Gate, drain, source. At the source we have 1 over GM2 impedance. This is V1. GM V1. GM V1. Which GM you will say? GM1. Then you will have lambda is equal to 0, so no R naught. In the absence of R naught, you are only left with RD. Where is the V out taken? Here is a V out. In this case, this V out will be here. Input is connected V in, right? Input is connected at this place. What are the two things that we can do? analysis wise, we'll first apply easiest one to do, KCL. What happens when you apply KCL here? KCL gives you, this is your ID current, this is your IL current. So ID is equal to minus IL, that is equal to V out by RD. And this ID is now equal to GMV1, right? Minus GMV1. So that is equation 1. So V out by RD is equal to minus GM1 by V1. Next, you have a voltage source, a resistor here. So we will apply KCL here, KVL. So when you apply KVL, what do you get? The supply V in. V in is equal to the drop across these two transistors. So V1 plus IS. What is IS here? This IS is equal to GM1 V1. IS times R, 1 over GM2. So that can be rewritten as V1 is common. So V1 times 1 plus GM1 over GM2. If you simplify and try to get V out over V in, right? V in value, when you substitute here, V out over V in, you will get simplifying, or the right terminology to be used is and simplification. On simplification, you get V out is equal to minus GM1 V1 RD, this equation. And the other equation will give you the V out is equal to minus GM1 RD times GM2 GM1 GM2 times Vn over GM2 plus GM1. Basically, to simplify, GM1 plus GM2 over GM2. So that fraction is here, only Vn substitute. Now, if you take V out over Vn, will give you the gain. AV is equal to V out over Vn equal to minus RD. This RD minus RD divided by 1 over GM1 plus 1 over GM2. It is easy to understand this one because now you're talking with regards to the resistance, right? So what is the resistance of the diode? 1 over GM2. What is the resistance of the device given here? GMRD. So you will get 1 over GM. RD is the resistance present here. So it is a ratio of resistance right now used here. Understood? Clear? So this is case 1 where channel length modulation was applied, negative for both. Now, what happens when I do the next one? We will work on case 2. What is case 2? Only one device has channel length modulation, other device doesn't have a channel length modulation. So that is case 2. Now we are going to the more practical scenarios. Lambda is 0 for M1. Lambda is non-zero for M2. In such a case, what will M2 become? M2 will show a degenerative impedance, and that degenerative impedance is given as 1 over GM2. That is already there. And because of the channel length modulation, you will have a parallel RO2. So this will be the impedance offered by the resistor, effective resistance that comes over here, the source load. So this is replaced as an effective resistance, which is given as 1 over GM2 by over R2. If you look at the channel length or the small signal model, it will be identical, just a small value change at the Vs. So Rs is going to be 1 over GM2 in parallel with RO2. Same GM-VGS, GM1 V1, this is V1. You will have no R0 here for the main device. Channel length modulation is 0 there. Here you will have RT. V out. V in is applied. So this is your small signal equivalent. Again, simple work. Apply KCL here. So KCL you will get it as V out over RD, that is strain current, is negative this current here, minus GM1 V1. Now here apply KVL. So KVL will give you this input supply Vin is equal to this voltage drop V1 plus this voltage drop. This voltage drop is given as I into R. I is GM1 V1 R 1 over GM2 parallel with RO2. Now if you simplify, since there is V1 on both sides, 1 plus GM1 multiplied by 1 over GM2 parallel with RO2. So Vin. When you simplify both of that, simplification gives gain AV, that is V out over V in minus RD, 1 plus GM1. Instead of just 1 plus GM2, now you just replace GM2 by RO2. So this is going to be the gain. Instead of just G1 over GM1 plus 1 over GM2 in the denominator, now this 1 over GM2 factor exactly having the RO2, the channel length modulation impact coming in parallel over here, right? So this is second condition. So what is the third condition? Right. Third condition looks something like this. In this case, you will have an output impedance here also, right? So this will be RO1. How will the small signal value change in that case? So this will be case 3. Lambda is non-zero for both M1 and M2. And how will that change itself? You will get two factors here. So along with this R0, you will get another GMB. GMB V1. So this is the other factor, and here you will get RO2 present here. So what is that value? So we will now begin. How do we begin? KCL again. If you apply KCL, we have one resistance. We got the second resistance output here. Third is the current here. So what is this ID? This current ID is the sum of all the three currents flowing through here. So GMB V1 plus GM1 V1 plus V0 by R out is equal to the current that is flowing here, V out by RD. So this is one equation. Now what will be the second equation? You will have KVL also applied here, KVL applied here. So V is equal to V1 plus, what is the current flowing? The current flowing is the sum of all the currents, V out by RD times 1 over GM2 in parallel with RO2. So you'll have to simplify. And on simplification, what do you get? KV is equal to RD times, so it will be minus RD divided by, in place of GM, you will have 1 plus GM1 plus GMB plus 1 over GM2 in parallel with RO2. This effective RD will now be RD. What it will be? RD parallel with RO1 and RO2. Okay, so that will be the output that you see here. Any intuitive analysis you got? Okay, now this is a diode connected, right? This next example, instead of this diode connection, we will apply a bias, meaning current source. So what will happen there? Let us quickly have a look. Progressively, we will change the example. Example 2. In this case, let us assume lambda is not equal to 0 for M1 and M2. There is VB connected here. There is a bias voltage. So when you have a bias voltage connected, this GM1 will get removed. Okay. So what does it look like? It will only look like a RO2. There is no GM1 coming into picture here. So if you find out the gain, the circuit will now look like one over RD, NMOS device with the input Vin, VDD, and this will be RO2. Here is the V out. This is the speciality of the circuit. What will happen here? This is the output here that you see. Since this is the load that we are applying and checking the output here. What does this look like? This is a constant current source. So this is R0. When you apply the small signal analysis, what happens? Small signal analysis is very simple for this one. GM1 V1, and there is R0 at the output, R01. Where is this Vout taken? Not at the drain, right? It's taken at the source of this device. So drain will be shorted. Here, the drain is kind of shorted. I will bring the Vout here. This is Vout. This is R02. Here is where you apply the input, V1. And this is your gate input supply. Clear? Now that you have developed this, first thing is apply KCL or you apply KVL. Easiest is KVL. By KVL here, this value is the sum of this value to the source. Vin is equal to V1 plus current through this I0 R0 will be given, or this value is Vout itself. That is one equation. The other KVL you will apply here. Apply this KVL. What is this value? What is the current and the resistor value? So the voltage across these two are the same, right? GM1 V1 into R02. Now if at this point, from this point to the current ground, there is R0. From this point to this, there is R0. So what does this mean? R01 is parallel with R02. R01 is in parallel with R02. So this is the R. Now what is the current flowing? G1, G1M, V1. GM1, V1, R0. What is this value is equal to? The value at this node. What is this node value? Vout. So this is the second equation. So if you want to find out from this, what is the GM value equation? GM1 is equal to Vout. You write it in terms of Vout minus Vin. So GM1 multiplied by Vin minus Vout, V1. GM1 V1 times R1 parallel with R02, R1 parallel with R02 gives you Vout value, right? So once you get that value, you can now simplify. On simplification, you get what is the gain. Just take Vout to the other side. So your AV is equal to Vout by Vin. That is equal to R1 parallel with R02. Now, since this term is there for Vin and Vout, you will find them in both in the numerator and in the denominator. In the denominator, it will come along with 1 over GM1 plus the parallel factor, R1 parallel with R02. So this is your gain. So what did you learn? This 1 over GM1 is only present in this. You're coming from the impedance that you're looking at here. And this is also a ratio of the impedances only. So there is GM1 factor does not play much role. If R1 parallel with R02 is a very large value compared to 1 over GM, then the effective ratio is 1 itself. It will be like a voltage follower circuit. So gain will be almost equal to 1. Now, let us look at what is the R out of the circuit, right? We'll find out what is the R out in a similar looking circuit. Just so that all bases are covered. Find R out. What does R out come here? What is the circuit? NMOS device. NMOS device. VB1, VB2. This is the ground, and this is this node. I want to find out what is the R out. Now let's begin with this circuit. Base is fixed, sorry, gate is fixed, source is fixed. So this is your current source, right? So current source will have RO2 in parallel. So this is our current source. Let us now build the circuit and see what is the impedance. Let's draw the small signal equivalent. What does the small signal equivalent look like? How do we begin? Simple. Start off with 3 terminals. GM1, V1. Then there will be GMB, VBS, which is again V1. Then you will get output resistance RO1. These are all together. Next value at the source. Source you have parallel resistance RO2 at the source here. You are seeing V1 and your input is applied nowhere. There is no input. It's all fixed bias. So this is grounded again. So what do we need to find out? What is the R out? So to find R out, we'll apply a test source Vx having a current Ix. R out equal to Vx over Ix. This is what we need to find. Apply the model here. Find out what is the value. We'll apply KVL here. KVL will give you this V1 plus Ix flows here, Ix also flows here. Ix RO2 equal to 0. This is one equation. Flow apply KVL on the same. So this Ix will now get divided into 3 currents here. So apply KCL at this node, you will get this summation, or you apply the KVL here. So if you apply the KVL, start with here Vx, then sum of these two currents plus this value Vx minus, or we can just sum it. Ix Ix RO2, right? You have covered this portion. Now find out this portion. What is that value? Ix minus these two currents, GM1 V1 minus GMB V1. Right? This current minus these two current is a current flowing through this resistor I. Now that multiplied RO1. So this is this. Now substitute V1 in this circuit with minus Ix R02, and then you get Vx over Ix here. So simplification gives you R out equal to Vx over Ax. This is given as Ax bring down, so RO2 is left over plus Ix times RO1. RO1. Now all the negative terms multiplied by a negative term here, so that will become all positive. What is that positive value? GM1 RO2, GMB1 RO2 times RO1. Take RO1 outside. This will become GM1 RO2 plus GMB1 RO2. So this is the total output impedance, right? So understood. Calculation is very simple. You just have to understand how to do it. So it's been 1 hour. Let me give you a 5-minute break, and we will start back on an important topic, which is biasing.